Welcome back. The last video we have seen vibration of a string in one dimension. So basically it is a one dimensional wave equation we solved when the string is infinite length or semi infinite length or finite length with boundary conditions and initial conditions. We have solved the vibration of the string problem. So we can also solve second order we can also solve two dimensional wave equation that is actually that models the vibration of a membrane or vibration of a drum. So if we will just demonstrate this vibration of a drum problem over a circular domain. So let us consider a drum which is like this, which is circular, so that we can use polar coordinates r and theta. Also when you have the vibration, so you can assume that it is radially symmetric. That means, so you have to give r and theta. So this is a plane domain. In this disk you have r and theta. So r is between 0 to big R and theta is between 0 to 2 pi. So theta is between 0 to 2 pi. So you can think of solutions that are not depending on theta. So that means if you know the solution on this line, this means you know it is everywhere it is same. So all along theta. That means, so whatever the curve you have on this, it will be repeated everywhere for every theta. So that means something like a circular shape of solutions. So if you look for when the drum is in the vibrating mode, that is what actually is reasonable to assume that you can the vibration, so that the displacement of a drum along is radially only, it depends only radially. So that means symmetric, radially symmetric solutions, it is a reasonable assumption. So we will try to solve second order wave equation over this domain, circular domain 0 to circle of radius r. That is the domain, spatial domain, and t is time, t is greater than 0. So we will try to see first what is the second order two dimensional wave equation. So two dimensional wave equation. So this is as usual the same. So utt minus c square uxx. So this is for the string. Now because it is involved two spatial dimensions, so what you have is 2 uyy equal to 0. So xy belongs to, this is if I include every region inside this disk, that is we call this dr is the disk, and this circle is called CR, I call it CR. So you have this belongs to dr. Okay, so this is what is this, and t belongs to t greater than 0. So this is the domain. So this is your second order, so two dimensional wave equation. Now if you give the velocity of this drum vibration at t equal to 0, so that is velocity and displacement of the drum, those are initial conditions. Initial conditions are u at x0, xy 0, this is equal to some function of xy. Similarly the velocity of the drum xy 0 is some g of xy. So this is what you have. So for all xy belongs to dr. This is the initial condition, that is what is known. So t equal to 0, you have the initial data and you have the boundary data, that is on the boundary you have this drum, that is that means normally see u at x equal to, so what happens on the CR, so u at xy and t equal to 0 for every xy belongs to CR. So this is what it means. So once you fix all along the boundary, so assume that the displacement of the drum or membrane is not 0, that means it is not vibrating, it is fixed. So this is the problem. So this is a boundary value problem we want to solve. Because you are solving over this circular domain, we can reduce this equation into polar coordinates. In polar coordinates, so we have the polar coordinates x r cos theta, y equal to r sin theta. So we want to reduce the spatial variables into these polar variables r and theta. So we have this, you have r is positive and theta is between 0 to 2 pi. So that is how we have. So, once you have this x and y, you have this is the one, and what you need is uxx and uyy. So, to start with ux. So, ux is, so u is a function of x y t. So, for the time being you ignore t, so you are changing only x y to r and theta. So, x y, if you replace r cos theta, r sin theta, u of x y t becomes u of r theta and t. So, if you want ux, you have to differentiate with respect to r and rx plus u theta theta x, that is what is your ux. Okay. And also there is another variable, that is ut into t of x. So, t is independent from the spatial variable, so that is 0. So, that is why this is ux is this. So, immediately you have the domain. So, dou x is equal to rx times dou r plus dou theta x times dou theta. So, dou theta. So, if you apply u, dou e by dou x is, that is what it is, you can get this. So, from this you can also get r is this, and you can get r equal to square root of x square plus y square under root, and theta is tan inverse y by x. Okay, so simply divide it, y by x will give you r tan theta. So, r goes, so that is simply tan theta. So, tan inverse of y by x is theta. So, you can calculate your rx and theta. So, rx and theta x. So, this will give you rx as what do you get, 1 by r 2 x, 1 by 2 r into rx with respect to x, you have 2 x, 2 goes. So, you basically x by r, x is r cos theta. So, this is basically r cos theta by r, that is cos theta, and you can also get theta x as 1 by 1 plus y square by x square, ddx of y by x is minus y by x square. So, this x square goes, that means you have minus y by r square. So, y is r sin theta. So, you have minus sin theta by r. So, you can write this as cos theta dou r minus sin theta by r dou theta. So, that is what is your dou x. So, now you can write your uxx. In the same way, you can also write uy. Uy is ur ry plus u theta theta y. So, this gives me dou y as ry. What is ry? Ry is, you can also get ry. So, ry is, r is square root of x square plus y square. So, ry is again, you can see that r, it will be sin theta. So, 1 by 2 square root of x square plus y square into 2y. So, that is 2 goes, y by r. So, y is r sin theta by r. So, that is sin theta. So, you have ry is sin theta dou r. You can also get theta y. Theta y is simply 1 by 1 plus y square by x square, ddx of dy of y by x is simply 1 by x. So, that will give me x by r square. So, you have cos theta by r. So, you have cos theta by r into dou theta is my dou y. So, now you can get your uxx, that is dou x of dou u by dou x. So, dou x, now I can get it from here. Okay. So, this is from dou x. So, you have cos theta dou r minus sin theta by r dou theta into dou u by dou x. So, from here. So, you can get it from, so dou, that is also simply you, so the same thing you operate on u, you get cos theta u r minus sin theta by r u theta. So, now cos theta is common. So, cos theta, now dou r you operate on to this function. So, you have, so cos theta cos square theta. So, dou r of cos theta, so these are two functions, one function, second function. So, this is a function of theta. So, this is 0 plus, so cos theta into u r r. So, cos square theta u r r. Then minus you have cos theta into sin theta. cos theta into sin theta. What you have is you have to differentiate with respect to r, which is 1 by r into u theta. So, you have u theta is also common. So, this is a function of theta function. So, u is a function of r also. So, you have to differentiate with respect to r as u theta by r. So, you have u theta r into 1 by r minus 1 by r square, that is the derivative of 1 by r. So, minus plus, so that will be plus anyway. So, that minus I have already taken. So, you are only differentiating with respect to 1 by r u theta by r. So, when you do that, this is what you have. So, into u theta. Okay. And then now you consider this part. So, this you act it on here. So, you have a minus sin theta by r dou theta of, so u r. So, now you have to differentiate with respect to theta for this function of x y. So, you have a u r theta cos theta plus cos theta is if you differentiate, that will be minus sin theta and u r into u r. So, that is what is this one, and minus plus, now you are acting on this one. So, you have sin square theta by r square u theta theta. That is my u x x. So, you have u x x as cos square theta u r minus 1 by r u theta r and 1 by r u theta r. So, this one together. So, you have, so that will be sin theta cos theta by r into u theta r. U theta r and u r theta both are same. So, you have sin 2 theta, 2 sin theta cos theta becomes that by r u r theta. This is what it becomes, these two terms, and what you get is this one plus 1 by r square u theta cos theta sin theta. Okay, cos theta sin theta, and that is what is this one, 1 by r square minus plus. Now, this one you have plus sin square theta by r u r plus sin square theta by r square u theta theta. This is my u x x. You calculate similarly u y y. So, that is dou y of dou u by dou y. So, again you do the same thing. So, if you do this one here, dou y is sin theta dou r plus cos theta by r dou theta, acting on sin theta, you have u r plus cos theta by r u theta. So, if you actually do this, sin square theta u r r, and this will be, if you, that is what is the, if you act this on this term. So, and this on this term, if you do plus sin theta cos theta, that is a common, and you are differentiating this u theta r. So, u r theta by r minus 1 by r square u theta, and that is what is the, this is a derivative. Now, you act this one on each of these, you have sin theta cos theta. So, you have cos theta by r. Now, if you differentiate this, this will be cos theta u r plus sin theta u r theta. And now, if you do this one here, so you have cos square theta by r square u, so cos theta by r comes out, r square dou theta of cos theta u theta. So, you have u theta theta into cos theta minus sin theta into u theta. So, this is what you have. So, you finally get u y y as sin square theta u r r minus, now look at this sin theta cos theta and sin theta cos theta, this term, these mixed derivatives, if you add, this will be simply plus sin 2 theta by r u r theta, and what you have is minus 1 by r square u theta cos theta sin theta, and here cos square theta by r u r, and this will be u theta theta. So, you have a cos square theta by r square u theta theta, and here you have a minus sin theta u theta by minus sin theta u theta by r square. So, this one and this one. So, you have a minus 1 by r square u theta cos theta sin theta. So, they miss something here. So, you have one more term here. So, you have this one. If you dou x here, when you operate this onto this, you have one more term. So, that is minus minus. So, what you have here is sin theta by r square dou theta. So, you have u theta theta sin theta plus cos theta u theta. So, this is what you have. So, you have extra term, that is sin theta by cos theta by r square u theta. So, you have two terms here. So, this one and this one. So, similarly here you have our last term is here 1 by r square cos theta sin theta u theta. So, you can see now u x x plus u y y is actually, now if you combine this one and this one together, you have u r r. Now, this gets cancelled if you add this, and this gets cancelled, and this one, this together will give me plus u r by r, and this will give me simply u theta theta by r square, okay, and this gets cancelled. So, you have this gets cancelled, okay. So, these are the things will remain. So, that is what you have. So, now the wave equation becomes u t t minus c square u r r plus u r by r plus u theta theta by r square equal to 0. This is now from r is, now if you take x y belongs to r. So, 0 is between r to r theta. So, theta is between 0 to 2 pi and t is positive. So, these are the three variables you have. U is a function of r theta and t, since u is this one. So, okay. So, is a function of r theta t. So, now if you consider drum which is radially symmetric, for radially symmetric vibrations, u of r theta t should be independent of theta. So, that means u depends only on r and t. So, if you do that, this is 0. So, what you have is the equation becomes u t t minus c square u r r plus 1 by r u r equal to 0. So, now you have the domain is between 0 to r, and theta is anyway. So, it is independent. So, you have theta t is positive. So, you have two variables, u is only function of r and t. Now, what happens to the initial conditions? Now, this is the equation. So, you have the initial conditions u at x y 0. So, at t equal to 0 for all r. So, u r 0 equal to f of r when r is between 0 to r. Similarly, u t at r 0 is g of r. Okay. So, this is what you have for 0, r is between 0 to r. And boundary conditions of the drum. So, you fixed it. So, this becomes, this is a capital R, that is the boundary of the drum. So, that is for all times 0. So, it is fixed. So, this is the boundary value problem you want to solve by separation of variables. So, let us use the separation of variables like we did earlier. So, the main purpose of solving this second two-dimensional wave equation in this domain is to extract a Sturm-Liouville problem for the Bessel equation that you have learnt in the Sturm-Liouville theory in the ordinary differential equations in earlier videos. Okay. So, let us solve. So, solution is for this problem, you consider u of let the solution be a separation of variables. So, you have r t, you consider like f of r, capital F, and g of t, which is non-zero. So, if you look for the solution as a non-zero solution, you substitute to the equation. So, what you have is f of r g double dash of t equal to actually c square, and u r r, that is f double dash of r plus 1 by r f dash of r into g of t. So, that is a common term in both the cases because it is only r derivatives. So, this because this is non-zero, you can divide it, so that you can write g dash of t by g of t if you divide with f or g t, and c square also you bring it here. So, you put it here, which is equal to f dash of r, f double dash of r 1 by r f dash of r by f r g r. So, this is divided by f r, f of r, g of t goes. So, this is the function of t left hand side, and the right hand side is a function of r. So, this should be a constant in the separation of variables method. So, you have this lambda is a parameter. Okay. So, now we have now if you consider this, this is one ordinary differential equation. So, what you get is f double dash of r plus f dash of r by r minus lambda f of r equal to 0. This is one ODE. Another ODE is g double dash of t minus lambda c square g of t equal to 0. So, this is for t positive, and this is actually for r is between 0 to capital R. So, these are the two things. Now, if you apply the boundary condition, so if you apply the boundary condition, what you get is u of r t equal to 0 will give me basically so f r into f capital R g of t has to be 0. So, g of t cannot be 0. So, implies because t is varying, so implies f of r has to be 0. So, this is your boundary condition, this is your ordinary differential equation, which is already in the Sturm-Liouville in the self-adjoint form. So, how do we see that is self-adjoint form? You have r into f dash of r, you can rewrite. So, r into f dash of r plus f dash of r minus lambda r f of r equal to 0. So, this is the equation. So, this you can write it like f dash of r times r, the old dash. So, p is r, p of r equal to, so implies p of r equal to r, q of r, what is that? So, you have a q of r is 0 plus q of r into f of r, that is 0, and you have lambda times w is w of r is r into f of r. So, this is what you have. So, immediately once you have the w in the Sturm-Liouville, you can define your phi j, phi and psi as an inner product, as a dot product. Dot product you can write like this, which is what is your domain? Domain is between 0 to r, capital R. So, you have 0 to capital R, and you have the w is this, that is a weight function r, phi r, psi r bar dr. So, this is what is your dot product from the Sturm-Liouville process. So, because already in the self-adjoint form, so all lambda should be real. So, this implies lambda is real. So, lambda is real, that means lambda equal to 0, lambda is minus mu square, or lambda is mu square with mu is positive. That is the meaning of real. So, you can choose any of these cases. So, start with the lambda equal to 0 case. So, if you choose, the equation becomes, this equation becomes r f double dash of r plus f dash of r equal to 0. So, this is actually your if you actually multiply, you can multiply both sides r, so that you can write r into this one. So, you can write you can rewrite this, just multiply r. So, that when lambda equal to 0, this is your equation. So, this is like x square y double dash plus x y dash equal to 0. So, it is a kind of Euler-Cauchy type equation. So, you can look for solutions f of r as r power m. So, if you look for solutions like this, so if you what you get is m into m minus 1 plus m equal to 0. So, that will give me m square equal to 0. So, roots are m equal to 0 and 0. So, you get general solution of that equation is f of r as c1 times r power 0, that is 1, plus c2 times, because they are repeated roots, r power 0 into log r. So, you have r power 0 is 1, you have log r. So, this is the solution. If you apply the boundary condition, that is f at capital R equal to 0 will give me c1 plus c2 log r equal to 0. Okay. So, this will give me c1 equal to minus c2 log r, and also what happens at r equal to 0, though it is a point of the drum, but it is not in the domain of your differential equation. So, that r, as r goes to 0, that is f of 0 has to be, so you cannot have, so u of, since u of rt, that is the displacement of this thing, that is you look for f r into g of t. For all times you cannot have u at 0 t, that is f of 0, that is the displacement, okay, f of 0 into g of t, it has to be finite. So, if this has to be finite, so f of 0 has to be finite, okay. So, f of 0 is finite. So, that is the actually another boundary condition. So, we have given only one boundary condition here, okay. So, one boundary condition is this, you can also say, and because r is the, so r is the singular point, you can give other boundary conditions. So, boundary condition, this is the one boundary condition 1, and the other boundary condition is f at 0 and f dash of 0, because r equal to 0 is singular point or finite or finite. This is my second boundary condition for the Sturm-Liouville problem. So, you have, since f of 0 is finite as the second boundary condition, you can see that log r, that is infinity. So, C2 has to be 0. Once C2 is 0, from this you can see that C1 is also 0. So, implies you have f r is completely 0 for every r between 0 to r, implies lambda equal to 0 is not an eigenvalue. Okay. So, we have to see what happens if lambda equal to mu square, other things. So, lambda equal to mu square, let us consider. So, then the equation becomes, what happens if lambda equal to mu square, if you put r double dash r f double dash, the equation is this, plus f dash of r, and what you have is minus lambda equal to mu square minus r mu square. So, minus r mu square f of r equal to 0. So, this is what is the equation. If you multiply r both sides, you have r times this, you have r mu square. Okay. So, you bring in a new variable. So, this is actually something familiar equation, but if you just use the, if you change the independent variable, r is the independent variable here. So, if you change this as a k, so new independent variable k, let k be r and mu. So, you try to change this. So, if you do this, f dash of r, so that is df by dr, you can write it like df by dk into dk by dr, that is 1 by mu. Okay. So, dk by dr. So, this is equal to 1 by dk by dr is mu times df by dk. So, similarly you can see that d square f by df r square equal to mu square d square f by dk square. So, that is how you see. So, you can substitute r square. So, r square is k square by mu square, that mu square goes. So, what you get is k square d square f by dk square, plus similarly, so you have k times df by dk minus k square f of, now f is a function of k now. Okay. So, just write f is a function of k, which is equal to 0, where f is function of k. Okay. So, f is a function of r after, so once you replace, r is actually depending, so f is depending on r is actually k by mu. So, mu is fixed to k by mu, since r is k by mu, so is f of r is actually f of k by mu. So, it is basically some function of k, mu is fixed. Okay. So, you can write if you want. Okay. So, f is depending on k, so you can say that f is as it is. So, f is depending on k. So, this is the equation we are familiar with. What is this equation? This is the Bessel equation. Okay. This is not Bessel equation, this is something similar to Bessel equation. Bessel equation is x square y double dash plus x y dash plus x square minus alpha square into y equal to 0. So, if alpha equal to 0, what you have is something similar, but we have a minus x square. Okay. So, let us choose alpha equal to 0 in the Bessel equation with alpha equal to 0. Bessel equation with alpha equal to 0. Okay. If I replace again do the same thing. So, I try to change let z be the new variable, new independent variable, instead of x here, if you convert this as a z, new independent variable, z is as ix, then you see that d square y by dx square, which is in this equation, becomes d square y by dz square into so simply start with like earlier dy by dx, dy by dx is dy by dz into dz by dx, that is I. So, you see that immediately d square y by dx square as d square y by dz square into I square. So, that is minus I square. So, that is what you get. So, you again I x square is z square by I square goes, the equation becomes now simply z square y d square y by dz square plus z into dy by dz. So, these two terms will not change like here with this transformation, plus x square. Now, I can write so where is the equation? Yes, you can now write the equation plus x square becomes minus z square, right. X square is because x equal to minus I z, so minus I square, right. So, what happens to minus I x equal to minus I z. So, x square is simply minus z square y of z, now is a function of z equal to 0. So, this is the Bessel, this is called modified Bessel equation with alpha equal to 0. So, with this transformation you see that the equation is modified. So, this equation is modified to something similar to here, this is exactly what you have here, you have there. So, we know that Bessel solutions are y at, so Bessel solutions, general solution of Bessel equation is C1 J0 of x plus C2 this is y0 of x. When you have n equal to 0, when alpha equal to 0, these are the two solutions. Y0, you will get a repeated roots. If you use the Frobenius method, you see that you get a repeated root. If you look back into the videos of Bessel solutions, when alpha equal to 0, what you get is this is the general solution. Okay. And at x equal to 0, r equal to 0, you want to have your solution to be bounded. Because of this boundary condition, you can see that this cannot be 0. So, the solution of this, general solution of this equation, the actual Bessel equation is, if you say that if you want your at r, if you want bounded, this is what is the solution. This is what is a function of x. If you want function of z, what is this one? This is a constant multiple of J0 of, instead of x, that is minus I z. This is what you have. So, y z is actually J0 of I z. So, if you write this J0 of I z, if you write J0 is C1 times, J0 is m is from 0 to infinity. So, instead of what you have is 1 minus 1. So, you know the formula of J0. So, that is now you have I z power 2m divided by 2 power 2m into m factorial into m factorial actually square. So, that is what you get, gamma of m plus 1, that is m factorial, gamma of m plus 1 is m factorial square. So, this is what you get. So, you can see that minus 1 power m and minus I power 2 m, okay, that becomes 1. So, what you see is this is actually C1 times m is from 0 to infinity minus 1 power m into minus 1 power 2 m. So, that is minus I square is minus 1. So, power m. So, the whole term this minus I z minus I power 2 m is actually equal to minus 1 power m, this together with this becomes plus 1. So, you have z power 2 m divided by 2 power 2 m by m factorial square. So, this is what is the equation. So, the general solution of the Bessel equation, and because of with this transformation this is what you get. So, that is this is exactly that modified Bessel equation is what we have here. So, the general solution is f of r, instead of z you write f of instead of r you are writing a k. So, you have a k. So, instead of z you are writing k. So, k is equal to C1 times this J0. So, I will just simply write J0 of minus I k, but J0 of minus k is this where, and plus C2 of Y0 of minus I of k, okay, but at k equal to 0 this is not bounded, okay, that we already know. So, this has to be 0. So, since y at f at 0 is bounded implies C2 is 0. So, for that reason I cancel this. So, implies f of k is C1 times J0 of minus Ik. Now, we have another condition f of r equal to 0. So, boundary condition 1 gives, this implies f of r has to be 0. So, that means C1 times J0 of minus I capital R has to be 0. So, this implies C1 times what is J0 of minus IR, you simply replace in this sum. So, you have a summation m is from 0 to infinity z power, that is r power 2m divided by 2 power 2m into m factorial square. This has to be 0, but you see that each of this in the sum terms in the sum are positive. R is, since capital R is positive, so this implies C1 has to be 0, because this quantity is non-zero. This is clearly each term is positive, this cannot be 0. So, implies C1 is 0. So, you found C2 is 0 and C1 is 0. So, finally, you get as f of k, which is equal to completely 0. What is f of k? F of k is the solution. If f of k is solution, f of r is also. So, you can go back to your new term. So, f of you can write your f of r. F of k is 0 implies f of r is also 0 for every r between 0 to r. So, what is your domain f of k? So, once you have this, because r is between 0 to r, k is between 0 to mu r. So, that is what is the your domain of this. Okay. So, what you have to write is actually boundary condition becomes f of mu r, f of mu r equal to 0. So, you have f of mu r is 0. So, f of mu r is, instead of, you simply replace with mu power 2m. Okay. So, r mu r equal to 0. So, mu r, so this cannot be 0 because mu is positive, r is positive. So, it implies this. So, you have fk is 0, and that implies f of r is also 0 in this domain. F of k is 0 in the domain between 0 to mu r, f of r is 0, that it means f of r is 0 in this domain. So, that implies mu square, lambda equal to mu square is not an eigenvalue. Okay. So, now we are left with only lambda equal to minus mu square. Minus mu square, if you see, the equation becomes f double dash of r into r plus f dash of r minus plus mu square into r f of r equal to 0. Okay. So, if you multiply r both sides, you get this and you have this. Now, you change the variable. So, again you use the same argument k equal to mu r, then change the independent variable r to k. So, what you get is k square f double dash of k plus k times f dash of k plus k square f of k equal to 0. So, this is what is the equation. Now, k is between 0 to mu r. So, this is what is the Bessel equation. With Bessel equation from 0 to mu r, there is the domain. This is your domain and this is the Bessel equation. You know the solution f of k, which is equal to C1 j 0 of, this is the Bessel equation with alpha equal to 0. So, you have j 0 of k plus C2, general solution is this. So, the general solution because this is the Bessel equation y 0 of k. So, again you apply the boundary condition f at 0 has to be bounded, implies C2, because y 0 is unbounded at k equal to 0. So, you have C2 has to be 0. So, and now you apply, now what happens, your general solution becomes C1 j 0 of k. Now, you apply first boundary, other boundary condition, that is f at r has to be 0. So, this means C1 j 0 of f at, what is your boundary condition, f at mu r equal to 0, right. F at mu r equal to 0, f at r in this domain, and because f at r is k by mu, right, f at mu r. So, f at r is actually equal to f at r is k by mu. So, f at capital R means equal to 0 implies f at k is actually, k you have to replace with mu r by mu equal to f r, which is 0. So, k the boundary is, boundary condition becomes this one in this domain after the transformation. So, C1 into j 0 of mu r equal to 0, and we know that j 0 function has infinitely many zeros on the positive x axis. So, you call them alpha 1, or because we use alpha, we can call this alpha 1, alpha 2, alpha 3 and so on. So, you denote them as alpha 3, alpha and so on. So, the roots of, let alpha 1, alpha 2, alpha 3 and so on are roots of, infinite roots of j 0 of x equal to 0 for x positive. Okay. So, this is what you have, alphas are all in the positive side of the positive roots, because this is defined, okay, defined between 0 to this thing. So, implies, so what is your mu? Mu is now varying, mu is positive. So, mu into r equal to alpha 1, if you consider, you call them mu 1. So, you have, so like that each mu I you denote, that is corresponds to alpha I. So, implies mu I equal to alpha I by r. So, I is running from 1, 2, 3 onwards, whatever denoted, alpha 1, alpha 2, alpha n and so on. So, this implies, so for which, so for these values of mu, you have j 0 of mu I into r equal to 0, because this is nothing but j of alpha I, these are the roots. Okay. So, that means C1 is, that implies C1 is arbitrary, you can take as 1. So, you have a non-zero solution. So, this implies the solution is f of r equal to f of k. So, the solution is, solutions are eigen functions and they are, and the non-zero solutions are non-zero, you have to say specifically non-zero solutions. That is, when C1 is, you take it as 1, when you take C1 equal to 1, you have j 0 of k, j 0 of k. So, j 0 of k, k is what, k is equal to mu r. So, mu I into r. So, mu I, so corresponds to this same mu I into r or eigen functions. I is running from 1, 2, 3 onwards. So, So, this is how you find your f of r. Okay. So, f of r is f of k by mu. Okay. F of k by mu f of k by mu. So, f of k is so let us write what is this what are they are, what are the solutions. You have f of k equal to j naught of k, f of k as j naught of k. Okay. What is k? K is mu r, k is mu r. Okay. So, what is f of r? F of r, you want f of r, right. So, you want f of r finally, not f of k. So, f of r is, so f of r is basically f of r equal to k by mu. So, this is j0 of k is actually mu into r. So, mu into r, mu into r. So, these are their solutions. So, you call them fi of r is, okay. So, you write like this. So, f of k. So, these are your solutions, f of k you call this fi j0 of I. So, you have if you so for each alpha I, for each mu I, your fi, if you denote for each I, you can define as fi of k as j0 of mu I into r. Okay. So, j0 into r. So, this implies f. So, this is running, I is running from 1 2 3 onwards. So, and then you can write fi of r as j0 of what is your mu I? Mu I is your alpha I by r into r. So, this is what you get 1 2 3 onwards. As a function of k, they are j naught of k, that is k is mu r. So, for each I, so each I, the solution is for each I, for each mu I, you have j0 of mu I r is the solution fi of k. So, if you want in terms of r, you have to write mu I. So, r is mu I is you can replace you can reduce k into r. Okay, it is already in r. So, you have to replace mu I as alpha I bar. So, these are the solutions, these are your non-zero solutions. That implies fi of r. So, it implies you have ui of rt, the solutions for each I, you have the solutions fi r into, that is j0 of alpha I by r into r. This is one solution into. Now, what is the other solution? That is g into g, you have g of t, g, call this gi of t corresponds to for each for each I, you call it g of t. Gi is satisfying the second differential equation here. So, the second differential equation is this. So, if you consider, put come back and put g double dash of t. So, lambda is minus mu square. So, you have a plus mu square into, so for each I, so you have mu I square into c square g of t equal to 0. So, you have g of t is c, you call this for each I, you call this a I cos mu I c t plus b I sin mu I c t. Okay, I is running from 1 to 3 onwards. So, because I for each is depending on, see g of t I am denoting also, g is depending on I. So, you have each I. So, g I is actually this, for each I is from 1 to 3 onwards. So, you know what is your g I of t and f I of t. So, go back and put it here. So, g I of t is j0 of alpha I by r into a I cos mu I C t plus b I sin mu I b t, mu I c t. Actually mu I is alpha I by r. So, you can replace this if you want. So, alpha I by r you can replace. So, alpha I by r, alpha I by r. So, implies, so this is true for every I equal to 1, 2, 3 onward. So, for each I u I of r t, that is the product of this solution and this solution, is the satisfying this 2 dimensional wave equation and the boundary conditions. So far we have not used the initial conditions. Now, like earlier, you make a superposition of this, let u be the solution. So, u of r t as a superposition of all this, I is from 1 to infinity, u I of r t, that is sigma I is from 1 to infinity. So, you have a I cos alpha I by r c t plus b I sin alpha I by r c t into this j 0 of alpha I by r capital R into small r. So, this is what you have, be the solution, be the solution, the general solution of wave equation with boundary data, boundary condition. Okay. So, if you assume this, one can show that it is actually uniformly convergent like earlier, that I am not proving. So, if you apply now, they apply the initial condition 1, initial condition 1 will give you u at r 0, u at r 0 equal to f of r, implies this will give me u at t equal to 0 cos t, that is 1 sin t will be 0. So, you have I is from 1 to infinity a I into j 0 of alpha I by r into r equal to f r. Now, I can get my AIs by simply integrate with use the dot product that we defined earlier. So, you get AI, you simply integrate both sides like this. So, you integrate from 0 to capital R and you have a weight function here r f of r times j 0, all these functions are real valued functions. So, bar does not matter, j 0 of alpha I by capital R into small r into dr divided by, now you are simply integrating this side from multiplying r j 0 of alpha I by r into r, this you are multiplying with itself, that is what only survives in this infinite sum. So, you have a square dr. So, this is what you get where I is this, for each I is from 1, 2, 3 onwards. So, if you apply initial condition 1, I can get my AIs like this in the general solution here. So, AI is known, which is this. Now, apply the initial condition 2. So, you have that is u t at r 0 is 0 is g of r, that is u t at r 0, if you differentiate this, this is the cos becomes and this becomes sin. So, this will go by and you put t equal to 0 after differentiation with respect to t. So, what survives is b I alpha I c r. So, you can see what you get is I is from 1 to infinity alpha I b I by r c. Okay. So, this is what you get into cos alpha I by r c t equal to 0, that is 1 into j 0 of alpha I by r into r equal to g r. So, again now from this if you apply one can see that b I. So, b I you can get it as not b I alpha I b I c by r, this whole constant I can get it as using the dot product, that is 0 to capital R, and you have a weight function r g of r into this eigen function, that is j 0 of alpha I by r into r dr, and left hand side it survives only integral r to r into j 0 square of alpha I by capital R into small r dr. Okay. So, this will determine your what is your BI. So, this implies this is r by c ci alpha c into alpha I, if you bring this r c alpha I the other side, this is what you get as BIs. So, I know what is my BI AI in this solution. So, that solves now, this is the solution as a linear, as a superposition of all the solutions in a separable form that satisfies wave equation, now boundary conditions and the initial conditions. So, this is the solution that we are looking for. Okay. So, this is the solution that is required here. So, this is how you solve the second order, this is how you solve 2 dimensional wave equation on a circular domain as in the form of symmetrically radially symmetric solutions that satisfies the boundary conditions. So, that means the vibrations are no vibrations at the boundary, and you have the initial data, that is you are providing as a vibration at time t equal to 0. You have the displacement of the disc, displacement of the drum or the membrane is 0 is given a priori, and its velocity is also given. That means vibration. So, displacement and velocity of the vibrations of the drum are given. Okay. Displacement and velocity of the drum at initially at time t equal to 0 is given. So, this is how you solve. So, the general solution now is nice in a separable form that you can see as a linear superposition of functions of r and functions of t. Okay. So, these are radially symmetric separable form of solutions for the vibrations of a drum. Okay. So, which is so that actually is the solution of a second 2 dimensional wave equation. Okay. So, we will see this is how we solve the wave equations in 1 dimension and 2 dimensional wave equations so far. So, we can pick up any other domain and make use. So, our intention is not just to solve 2 dimensional wave equation in other domains. Only main purpose is to make use of the Bessel equation that we have derived in the ordinary differential equations earlier. So, this is how we can solve this just to demonstrate the solutions of 2 dimensional wave equation in a simpler domain like circular domain, okay, as an application. So, next in the next video we will see how to solve, we will move on to heat equation. So, again like for wave equation, like in the wave equation we try to solve the heat equation in the infinite case, infinite spatial domain, that is you consider an infinite rod. Infinite rod, you give the initial condition that you, because it is in the heat equation you have only time derivative is 1, you have to provide only one initial condition and you provide the initial data. So, with this initial data heat equation you are trying to solve in the full domain, and then you can also do the semi infinite domain and then onto the finite domain, that is you can think of finite rod. So, we will just see that how the solutions of the heat equation will be in the next few videos. Thank you very much.